All right, this lecture is going to deal with SI units. SI units are essentially in French, System International, or we commonly in English call those the International System Units, and known to most of us as the metric system, as I learned it in grade school. Um, all right, so that's what we're going to do. We're going to get through that. Let's go to the next slide. All right, so the way it works is the SI units or international system units defines two types of units. One are the base units. These are for fundamental quantities like mass, time, and length, for which you can't really define them as a function of any other types of quantities. So that's what makes them like fundamental quantities. Other units are derived units. They're quantities that can be derived from these fundamental quantities like mass, time, and length. And examples of those might be, for example, force or work. So a Newton is a unit of force that causes a 1 kilogram mass to accelerate to a acceleration of 1 meter per second per second. That's what we have down here at the bottom, you see. So you can see that the Newton is basically being defined as a function of these basic fundamental quantities of mass, time, and length. The same thing for basically a joule, which is a unit of, it's a unit of work. It says unit of force. That's incorrect. It's a unit of work where 1 Newton force is displaced for a distance of 1 meter in the direction of the that the force is actually applied. All right, so keep that in mind. You have your base units and you have your derived units. So here are the base units. There's 3, 4, 5, 6, 7 of them. The most commonly used ones are length, mass, and time. That's what we have in the first column, the dimensions of length, mass, and time. And the units in this third column would be, for example, meters, kilograms, or seconds. And then the next one down is basically electric current, which is going to be in units of amperes. And you can see the abbreviations here on the right-hand side. So we have abbreviations of meters, kilograms, seconds, A for amperes, K for degrees Kelvin. We'll talk more about that. CD for candela. That's essentially how intense light is. And MOL for moles, which is really the amount of a substance. Probably if you had chemistry, you're probably familiar with that quantity. All right, so this is all of both the base units and the derived units. And the derived units can be divided up basically into two different groups. We have here this group over here, and I'll just draw a circle around that. These are the derived units without special names. So volume has units of meters cubed in this case. An area would have units of meters squared, and a velocity would have units of meters per second. There's no name for meters per second. On the contrary, we have our derived units with special names. That's all the ones here on the right-hand side. So, for example, and we talked about this in one of the previously, a Newton is a unit of force, and it has units of kilograms per meters, kilogram meters per second squared. And the joules has units of Newton meters. Or, and again, as I pointed out before, you could apply the units kilogram meters per second squared times meters, because the newtons, we can just substitute in that value. So here, there are other values such as degrees Celsius down here, which is probably our more conventional way of representing temperature. Other things like power is in watts, pressure in pascals, and a number of other values. Some of these are for electricity, such as capacitance, resistance, and conductance, which has units of farads, ohms, and I'm not familiar with, Siemens, excuse me, I am familiar with that. So these are the derived units. So again, base units on the left, derived units with no special name on the middle, and then we have all these other derived units with special names and symbols. All right, so let's talk about a few of these. One you might not be familiar with is degrees Kelvin. It's a way of representing temperatures. So the freezing point of water we know to be 0 degrees Celsius. That would be equivalent to 273.16 degrees Kelvin. The boiling point of water, 100 degrees Celsius, equivalent to 373.16 degrees Kelvin. So we see that essentially the magnitude of the change of 1 degree is essentially the same as the change in degrees Kelvin. So we can use this kind of conversion down here where you'd say whatever your value in degrees Celsius, so say you have y degrees Celsius, you simply add 273.16 and you end up with the temperature in degrees Kelvin. If you have had physics, or when you have physics, you'll learn more about degrees Kelvin and why it's an important quantity. All right, the amount of substance, this is essentially, if you've had chemistry in this case, you're probably aware that the number of particles in a mole is 6.023 times 10 to the 23rd. 10 to the 23rd, you know, would be like 10 times 10 times 10 times 10, 23 times. So you can imagine that is a big, big number. If you have that number of atoms in your hand, then that weight is simply the atomic weight in grams. So for example, we know that the atomic weight of carbon is 12. So 1 mole of carbon atoms is going to be equal to 12 grams. Okay, so that's all that is, and it's kind of a fundamental property that you'll learn more about in chemistry, or you may already know about. All right, so here again are just the derived units that we were talking about before. We have newtons. 1 newton equals 1 meter kilogram per second squared. A pascal is essentially equivalent to 1 newton per meter squared. And the joule, it's a unit of work, equals 1 newton meter, or 1 meter squared kilogram per second squared. And the second quantity is found by essentially taking this and substituting that into this quantity here. All right, derived units without special names, we're just reviewing. There are these acceleration, velocity, area. These are all defined basically based on the fundamental quantities. So for example, velocity would be most likely to be represented as meters per second, and area would be most likely represented as meters squared. All right, liters is an acceptable SI volume unit. A liter is about a little more than a quart, for those of you that are familiar with SI units, or excuse me, US customary units. And 1 cubic meter, that would be like a cube. That's 1 meter by 1 meter by 1 meter, will hold 1,000 liter volume. And 1 milliliter, just so you know, is also equal to 1 centimeter cubed. Okay, it's just something to remember. It sometimes comes in handy. All right. SI units also allow for certain kinds of prefixes to be applied. So, for example, and the prefixes essentially multiply by a factor. So if we took this one, which is milli, or let's start with, kilo. So let's say we want to apply kilo. It's a factor of 1,000, or 10 to the third, to grams. So we'd say 1 kilogram equals 1,000 grams. The same thing we could do with a pico. So if you have 1 picogram is going to be equal to 10 to the negative 12th. That's what this is. That number of grams. So that's like a very, very small quantity. So you can see these are really set up to help you to represent both like very large and very small quantities without having to write things like this over here, this value with all these like zeros and then some numbers in it. That's what the prefixes are really good for in the SI prefixes. The ones I showed you here are the ones that, in my own estimation, are the most commonly used. There's actually, there's 1, 2, 3. I showed you 7. There's actually 21. And there's some kind of odd ones in here that, like, let's say you want to know the distance between 2 electrons. And I don't know if this is true, but let's say it's equal to 1 septillionth of a meter, which is 10 to the negative 24th of a meter. You would say it's 1 yoctometer. Likewise, they have some odd ones at the high end. Let's say the distance between 2 galaxies, for example, is 1 sextillion, which is 10 to the 21st meters, for example. Then you would say the prefix name is zeta, and they show you how to pronounce it here, and they use a Z. So it would be like 1 ZM equals 10 to the 21st meters. So there is a table like this in your textbook, so you can take a look at that. This is just an example of 3 quantities, so 1 kilogram, where we're going to apply the K. Remember, the factor is a 3. So we end up with 1,000 grams. For centimeter, we're going to apply a factor of 0.01 to meters. So we end up 0.01 meters. And then for milliliters, 1 milliliter, remember the factor is 0.001 liters. You may not remember, but you can always check the table to see what these are. So this is just some examples of how the prefixes are used. In a minute, we're going to use these kind of factors to convert from one set of units to another. All right, so there are some rules about writing quantities in SI units. Always put a space between the numbers. Don't write 5M like right next to each other. Write 5 space M. When you have 2 units in their product, you can put a dot like that, or you can leave, like that, circle that, or you can just leave a space. In this case, you see there's a space between them, that means it's a product. So be careful if you don't put a space, like this, then the M becomes a milli, and S would be seconds. But if you put a space like this one, this is an entirely different thing. This is essentially 5 meters product times seconds. The product, a meter in seconds. All right. When you're using a fraction of 2 units, you can use a slash. Any one of these are appropriate. You can use a slash. You can use a fraction style, or you can do it this way. Meters, seconds, inverse. So that -1 exponent applied to S is basically 1 over S. And the last thing to be aware of, be careful of ambiguous terms like mkg/SA, because where you don't really know where this A goes. Is the A part of the same line with the M, or is the A basically underneath this fraction under the kg? So it's better, make sure if you're going to have a quantity like that and you want the A to be underneath, then put it underneath like that. Use the parentheses. And put it, now we know it's under the fraction. If you put A, say on the other side, put the A over here, then we know that it's part of the upper line of the fraction. So it's always good practice to look at what you're writing, make sure that there's no ambiguities in it. All right, so we're going to convert these following quantities one at a time. And I'll show you how essentially, and these are essentially get a little more complex In another lecture, we're going to be converting from SI units to US units and reverse, and that's a little more complicated. So we're going to start with these. It'll give you a little practice on how to do conversions. All right, so the first one we're going to do is a very simple conversion from 0.05 grams to milligrams, okay? So what is the appropriate conversion factor? We know, so we need to convert from grams to milligrams. So we know that 1 milligram is going to be equal to 0.001 gram. That's just by definition of what that milli prefix is. It's 0.001 grams. So then we can, if we want, divide either one of these on both sides by the same value, and I'll show you why we want to do that. So let's say we're going to divide by the 0.001 grams. So we're going to end up with 1 milligram over 0.001 grams equals. So what happens when you divide 0.01 grams by itself? You end up with 1. So that's telling us something really important. It's telling us that this quantity on the left-hand side over here is essentially equal to 1. So we can multiply that by anything and end up with our original value without changing the value, in other words. So imagine that we have a mass of 0.05 grams. We can multiply by that conversion factor. So let's do that right now. We end up with multiplying that by 1 milligram over 0.001 gram. And if you look at it, 0.05 times 1 is just 0.05 divided by 0.001. So what is, we know this is 1 over 1,000. So that's like multiplying by 1,000. So it's simply going to end up with, we're going to move the decimal point in this number here over by 3 places. So we're going to end up with 50 milligrams. And to make sure that you did the conversion factor right, that you applied it right, it's always important to go to your equation or where you applied the conversion factor and start canceling units. And that's that G cancels out with that G. And all you have left is milligrams. So in fact, we did it right. Sometimes it's a common mistake that you'll take a conversion factor like that. You may have written it differently. You may have written 0.001 grams per milligram and multiplied it, and then they would not cancel out correctly. So we found, in fact, that the mass, starting with 0.05 grams, is in fact equal to 50 milligrams. All right, the next one. This one's a little harder, and I'm going to rely on scientific notation to get this one right. So what conversion factors do we need in this case? We need to convert from kilograms to grams, and then from grams to micrograms. This unit here, this letter here, is called a mu, and that is essentially a micrograms. And I'll write down, you may not remember, if you have to, you can always go back to the table or look in the textbook. And what you'll find out is that 1 kilogram equals 1,000 grams. I think we all remember that. But the harder one that you probably don't remember is that 1 microgram. I always have a hard time writing that letter. That's a mu equals, I'll write it out the long way first. 3, 4, 5. 1, 2, 3, 4, 5. 1 grams. So you imagine that's a really small quantity, and it's easier to write it as 10 to the negative 6 grams. Scientific notation. Always use scientific notation if you can. In fact, it's nice. We could even do that for the kilograms. We can say that's equal to 10 to the third grams, and we'll use that, in fact, when we do our conversions. Now, I'm not going to, in the previous slide, you remember I divided it out the values, and then I showed that that conversion factor equals 1. I'm not going to do that. In this case, I'm going to just go right ahead and write the conversion factors. So in this case, so what is 0.0? This number is 1, 2, 3, 4, 5. 5 zeros. It has a decimal point, 5 zeros, and then 1, 3. That equals, in fact, in scientific notation, and I'll write here mass equals 1.3 times 10 to the negative 6 kilograms. All right, so that's what that is. So now we're going to apply our conversion factors, and I'll apply the first one, which is 10 to the third grams per kilogram. So I'm going to write here 10 to the third grams per kilogram. This is nice because we can see the kilograms are going to cancel out. And for the other one, in this case, we're aiming for micrograms, right? So we want to have the micrograms in the numerator, not in the denominator. So in this case, I'm going to say 1 microgram over 10 to the negative 6 grams. So now we see, let's look if they cancel out correctly. Kilograms, kilograms, grams, grams. We're going to end up with just milligrams, okay? Now, what can we do about multiplying these out? You can see 1.3 times 10 to the negative 6 times 10 to the third. We just add the 3 to the negative 6. So we end up with 1.3 times 10 to the negative third. And then we have a negative 6 in the denominator, so we're going to add on a 6 there. So negative 3 plus 6 is going to be a positive 3. So it equals 1. Let's go back to our black color. Equals 1.3 times 10 to the third micrograms. All right, so that's what our mass equals. All right, this one has another kind of complexity to it in that we don't know how to get from cubic centimeters to cubic meters. We do know how to get from cubic meters to liters, and I'll write that one first since we know that one. We know that 1 cubic meter equals, let's erase that and make that a little neater. 1 cubic meter equals 1,000 liters. All right, equals 1,000 liters. And so that we know that conversion factor. And we know that, how do we get from meters to centimeters? So we'll put meters on this side. We'll say 0.01 meters equals 1 centimeter. Okay, so we have those two conversion factors. And we're going to apply those to do this conversion over here, 30,000 cubic centimeters to liters. So cubic centimeters is, we have centimeters, it's like a very small cube that has 1 centimeter on each side, but it's a volume, equals, and I'm going to do this in scientific notation. I love scientific notation. So what's 30,000? That's 1. I'm going to do this in red so you can see it. 1. And so we go over 1, 2, 3, 4. I don't know if you could see that. 4. Anyways, we're over here. It's equal to 3.0 times 10 to the 4th centimeters cubed. All right, put that in parentheses. And now we're going to apply a conversion factor to get you from centimeters. I forgot. We need to get this quantity in centimeters cubed. So let me do that over here, if you don't mind. And I'm just going to do is I'm going to take the cube of both sides. And I'll do it first to the right-hand side. We're going to end up with 1 centimeter cubed, because 1 cubed is 1. 1 centimeter cubed. What are we going to do on the left-hand side? And again, I'm going to use scientific notation. This quantity here, 0.01, that's 10 to the negative 2. If we cube it, we just take that negative 2. It's like 10 to the negative 2 times 10 to the negative 2 times 10 to the negative 2. We're going to take negative 2 plus minus 2 minus 2, negative 6. So that's going to be equal to 10 to negative 6 meters cubed. Okay, now we have a conversion factor that we can use. So we're going to use that conversion factor here. And I'm going to write 10 to the negative 6 meters cubed per centimeter cubed. And then I'm going to apply this other conversion factor. It's very messy here, but 1,000 liters per cubic meter. We know, for example, I'll switch to red. And red. Centimeters cubed. Centimeters cubed. So now we're just in meters cubed. And we know 1 meter cubed equals 1,000 liters. So we're going to multiply 1,000 liters times, over 1 cubic meter. All right, and does this cancel out? Yes, it does. Cubic meter. Now we can multiply these all out. And because we're in scientific notation, that makes it really easy. We didn't make this 1,000 scientific notation, but we know that's 10 to the negative, 10 to the third. So we're going to add up all of our exponents. So we have a 3 here, minus 6, that's a negative 3, plus 4 makes a positive 1. So we're going to end up with 3.0 times 10 to the first liters. That's our answer. And we'll just write it in a more conventional way that you're probably more used to. Equal to 30 liters is our volume. That is the answer for this problem. All right, this is an interesting quantity, 100 milligrams. We wanted to convert it to kilograms per cubic meter. What makes it interesting? Because it's a mixed units, milligrams per liter. So it's a mass and a volume, mass per volume. So what might be a mass per volume? It might either be a concentration, like the amount of, say, salt in water and is dissolved in 1 liter of water. Or it could be a density, like the number of milligrams of mass of some material, like plastic or rubber or anything, per liter volume of that material. So it could be either one, it could be either a concentration or a volume that's being represented here. Keep that in mind. So we're going to go from milligrams per liter to kilograms per cubic meter. We need 2 conversion factors in this case. In fact, we actually need 3, because we're going to go from milligrams to grams. And then we're going to go from grams to kilograms. Okay, so let's write out what we know, which is that 1 milligram equals 10 to the negative third grams, right? And I'll just write it over here just for those of you that are confused about what that means. 0.001 grams. Okay, but it's easier if you write it in scientific notation, so keep that in mind. And we can write that 1 kilogram equals 10 to the third, 10 to the third grams equals, in this case, it's going to be 1,000 grams. All right? So those are our mass conversion factors. And then the other one we need is we're going to need 1,000 liters equals 1 cubic meter. All right? So if you have a cube, 1 meter on a side, basically you can put 1,000 liters of some volume in that cube. All right, those are conversion factors. Now we have, I'm going to say it's a concentration. I'll just use the letter C, equals 100 milligrams per liter. Now we're going to use our conversion factor. So the first thing we're going to do is make it into grams per liter. So what we'll do is we'll say, we're going to use this first conversion factor up here. We're going to say 10 to the negative third grams per milligram. And then this one is now, so we're in grams, but we actually want to get into kilograms, right? So next thing we're going to do is we're going to apply this conversion factor, which is 1 kilogram per 1,000 grams. Oops, I was going to use, let me switch that to, we'll use scientific notation since I've been telling you how great it is. So it's going to be over, oops, try that again, 10 to the third grams. All right, that's our second conversion factor. And the last one is we need to go from liters to cubic meters. So now in this case, you see the liters is in the denominator. So in the conversion factor, we're going to want liters to be in the numerator so that they're going to cancel out. And then we're going to end up with liters, and we're going to end up with per cubic meters. So the conversion factor, I'm going to write it this way, 1,000 liters per cubic meter. Now let's see if they all cancel out. I know they do. Milligrams, milligrams, grams, grams. And then over here, liters. And the last one here is liters. Perfect. Excellent. All right, so let's see what we end up with. 100 is 10 to the second. Let's write these out so you can all see this. Oops, let's do it in black. So we're going to have a 10 to the second times 10 to the negative third. And then here we have 10 to the third in our denominator. So that's, I'll write it here as 10 to the negative third, just to keep them all consistent. And the last one's 1,000. That's 10 to the third. Oh, great. So 2 minus 3 is negative 1. Negative 4. Negative 1 is what we're going to end up, plus 3. Let's see it. So it's 5 minus 6. Yeah, negative 1. So we're going to end up with 100. Oh, nope, that's right. Negative 1. So 10 to the negative 1 kilograms per cubic meter. Or we can write it in a more conventional way, 0.1 kilograms per cubic meter. And that's what our concentration is.